Okay. All right. Thanks for the nice introduction. And definitely, I'm excited to talk to you all. I went to your. Can you see this top bar on your screen? Do I need to get rid of that?
Yes.
There we go.
Oh, that doesn't show for us, the Zoom bar. Yeah.
Okay. Yeah. So I visited your GitHub site, and yeah, I was really excited to see some of the things. I was unaware of some of what's going on in this group. So this is. I hope this builds some more conversations that we can continue on. So I'm Zac Ward from Oak Ridge, and we're going to be talking about kind of breaking symmetries in these compositionally complex oxides, or the high entropy oxides. And so to get started, I want to make sure that I point out the people that are actually doing the work that I'm going to talk about today. So these pictures on the right here, these are postdocs that have worked in the group and worked on this project. In particular, Yogesh was with me when we first got started, the first films that were grown, and Alessandro, the new work, he's moved on to Los Alamos now, but we're still closely collaborating, and I would expect to see a lot more coming out of him. He's really fantastic. All right, so I'm going to tell you quickly what I do and what my expertise is. I'm a thin film synthesis guy on correlated oxides, and I use pulse laser deposition as my main synthesis technique. So that means I'm making ceramics, but I typically don't do a lot with those other than use them as a target to shoot a laser at, and that's going to allow me to grow these single crystal films. We do some ion implantation, and then within our lab, we do the standard X-ray diffraction, squid magnetometry, and electron transport. We do a little bit of microfab if we need devices, and then, of course, simple scanning probes just to check what our surfaces are looking like to make sure we've got nice, clean surfaces. And then these environments, we do have an Oxford system that'll get us down to 10 millikelvin. I'm not going to talk about anything today in that system, but we can also get up, up close to 1000 C. Magnetic fields, plus or minus 14 Tesla, and then a range of pressures. Okay. We also we've usually got multiple user projects running throughout the year, and these are APS and Brookhaven. And we're doing things like XAS and Zane's, RICS, XFs to try and figure out both what the composition are, what charge states are of the materials we're making. Then we do, being at Oak Ridge, we do a lot of neutron diffraction and reflectometry. And of course, the microscopy that's done either with collaborators here at Oak Ridge or through user proposals at other labs. All right, so disorder. This is what we're going to talk about today, and this is what's exciting about talking to this particular group is you all are kind of putting together a coherent way of addressing this in materials. So we know disorder is important, especially in correlated systems. When we think of disorder, one of the problems that I've had both with funders and going through review is when you say disorder, people think of that as a bad thing. And so what they're typically thinking of is you've got a bad material that you're looking at, whether that's vacancies or some glassy structure or something like this. So that's not what I'm talking about. What I'm talking about is something where you can actually control continuous, in this case, I'm going to call it continuous crystal and positional symmetry. So you've got your crystal, but then on those different lattice sites, you either, you have a mix of elements and or the parameters that those elements have may be disordered. So something like
just one short question related to that. Why do you exclude vacancies? You think that vacancies, this is similar to an alloy. You can have vacancies in an alloy still crystalline.
Yeah, I'm not. So I'm going to say that we were talking about those extrinsic effects. And so these are things I want to try to make a perfect crystal. And when I say perfect, I mean, I don't want vacancies in there. Certainly we're going to have them. It's just impossible in a real material not to have them. But my goal is to reduce those to the point where if you're trying to do a calculation, that's not a dominating effect, right? So on the disordered systems, you can also think of like spin glass is also something where you have a disordered, positionally ordered crystal, but you still have some disorder. In this case, what the spin component is. You could try and stretch it out to maybe ferroelectrics where you have a sublattice that's doing something different. Or these trimeron sort of things. This is a Fe3O4 system where you have delocalized electrons that are ordered locally, but then disordered macroscopically. This setup is actually really exciting and something we're following on more deeply now in some other systems where it looks like in these high entropy systems, you can get these interesting local delocalization of electrons that give you some new behaviors. Okay, so if we're talking about that, we've got really two control parameters that we can set, hard set. And so that's, you can control your crystal lattice. So we want to make a material that, whatever the crystal lattice is, we want that hard set into our single crystal film. And then the other control is, what are the strain, what kind of pneumaticity may be in there. So what we want to tune then is thinking about whether you have the spin state, this disordered across the lattice, a charge, the orbital, these fundamental parameters that are disordered across the ordered crystal lattice. So what we want to do is we want to try and maintain the positional symmetry and manipulate that site-to-site order parameter, whatever that may be that we're trying to tune in. All right, and it's kind of a background to some of the challenges of this. So I'll start off with the way that we've always done things. So if you say you have one material and a structure, another material, within that material, it has some type of coupling or some kind of interaction that happens between. Another material may have a different type of interaction. And so if we think about this in terms of what the microstates are doing, you basically, in this system, you have two separate systems, two separate microstates that are present on that system. What we've done with heterostructuring, so coming from thin films background, what I often will do is create a heterostructure so that I can force those two materials to interact with each other at an interface. And so you can kind of picture this. Often what we're doing is we're putting in all this effort just to try and get this kind of composite state here at the center. And that gives us, of course, a lot of interesting new physics to look at. If you want to go through and control this, so let's say you want to hit perfectly, design a material where you get a certain type of coupling between the system, you can think that you're going to create something like this where, you mix 50-50 each type, and that'll give you some sort of uniformity of state. But of course, in the real world, if you try and mix two different materials with each other, you end up getting some random distribution as those things are forming. There's some few exceptions to this, of course, like intermetallics and things, but we're going to talk about oxides today. And so if we think about this in a real system, what you're aiming for is you're going to get some distribution of microstates. And this is exciting because this gives you a lot more competition and dynamics in your system that you may be able to find some new physics there. The problem, of course, is that with just two elements, it's really not realistic. And that's because this is synthesis limited. And this is more of a material science problem. But the reason this is, if we've got our phase diagram here, let's say we've got element A and it forms some parent phase that it's happy in this alpha phase. You've got element B, it forms some other phase. You can dope a little bit of B into A and maintain this crystal structure, but it's actually a very narrow window. And you can do the same over here. You can put a little bit of A into B and maybe move a little bit around in that phase space. What we want is something that's really disordered so that you can get the full range of those microstates. But that doesn't happen. What you end up with is something where you have these mixed phases. You get clustering, and so you'll basically get a little bit of the two different phases, but that's all you get. You're not reaching that middle ground. And the reason is the mixing is basically driven by enthalpy in this point. And so what we want to try to do is get to this term over here, where we can get the entropy at play, which will allow us to maximize the mixing and hopefully get to this well-mixed state. Okay, so this is where the high entropy alloys came in. And so this has been almost 20 years now. And so these are generally constructed 5 or more. These are going to be metal-metal bonded elements. And they're a relative few. This isn't the entire periodic table that people have made these. And there are 4 basic structures that you're going to find these somewhere. So you can't access really complicated crystal structures. And I'm going to say, maybe somebody can correct me, but I still have not seen an example of large single crystal synthesis being possible. You might be able to get a single crystal phase, but there is some segregation, tends to be some segregation in how those elements are distributed through the crystal. And so I'm going to say that that's, from my perspective, looking at fundamental properties, that's going to limit your predictive ability to control these things because there are these extrinsic effects. So here was a paper that came out from Tina and JP Maria. This was the first example of these high entropy oxides. So now what we're going to do is we're going to put an oxygen, this anion sublattice in there, and that's going to give us some new and exciting things that we can go after. So if we think of the high entropy alloy, how the metal-metal bonding works, basically your electrons are kind of smeared throughout the system. The high entropy oxides, you basically put this oxygen sublattice in there that greatly increases the number of microstates you have, but it also does something exciting with localizing electrons. And so for those of us in the correlated system, like this is something that perked our ears up and got us involved. So a simple way to picture this is, this is going to be that rock salt that we had with these five binary systems are going to be mixed up, and you can see their parent phases are different. You mix them up, and if you heat them up, the entropy kicks in and everything starts to mix around and you can get a nice single phase of this. If you slow cool it, it separates back out and you get these clustering of the parent phases, like we said was the problem before, even with the binaries. But if you fast cool, if you can quench this, you can actually lock in that entropy stabilized state. So the way that we do this, and the way that we have been successful in creating the first single crystals of a lot of these materials is using pulse laser deposition. And so this is just a kind of a diagram here. What we're going to do is we've got a ceramic target down here. We're going to have our substrate up here that we're going to grow on. We can have our process gas that we can control here. We're going to bounce an electron beam off the surface, watch the read intensity. This tells us what our surface is doing, so we can make sure that we can monitor in real time as we're growing how that surface is evolving and what crystal structure we've got. And then of course our excimer lasers are going to come in here and blast this target. So I'm going to show a quick video in case you all haven't seen. So this is looking inside. This is about 5 centimeters from here to our sample. Our electron beams coming in here, bouncing off to this screen over here. Laser's going to come in, blast our target, and then that material is going to move up. So that pulse width is about 20 nanoseconds, 50 nanoseconds, somewhere in that range. And then it only takes a few milliseconds for that plume to go from here to our substrate. That is basically, that's an ultra fast quench that's happening. You're in non-equilibrium state, you fast quench that, and that's why we're able to get this really exceptional mixing on these materials. Okay, so some of the most exciting things in the correlated systems happens to have very complicated crystal structures. And so this is where we want to get, this is where our goal is, to be able to make these more complicated structures with high disorder, high compositional disorder on one or more sublattices. But I'm going to show, when we got started, what we want to do, let's just start simple. Let's do a perovskite. We're going to put the training wheels on it and see if we can make this thing. So this was Yogesh Sharma. This was, he was the first, we were working through this. He was the first one to grow these materials. And so what we're going to do, this is basically, you can think of it as a barium titanate sort of analog, but we've added 4 more cations on that B site. And here we've given examples where we've grown separate thicknesses on a strontium titanate. The full width half max of the rocking curve, very sharp, only slightly broader than the substrate. So this is all to say that this is a very nicely ordered, clean single crystal film. And when we do the TEM on this guy, we get very nice crystalline structure. You might see some slight discoloration, these light colored blobs here. That's actually from the processing. That's not a difference in the density. That's the processing had a little blowback on there. And you can tell when you zoom in on these things, you can actually see the ordered state. And if we do eels on that, you'll see that those cations are evenly mixed on the sublattice. There's no clustering there. So that's what we were aiming for. And in this first paper, the only functional thing that we really did with this was we assumed, well, if we've got all of these different cations in this thing, then we would expect the phonons to basically be damped out and not move heat well. And sure enough, we did this TDTR technique, which allows us to look at the thermal transport. And what we saw is that thermal conductivity was very close to what the amorphous limit was. And so this is, you've seen the crystalline structure, and yet we're very close to the amorphous limit. So here we've got a means of really damping out those phonons. Our initial guess was it was the difference in mass. It looks like there was a paper that came out probably about a year after this, that suggested that really it's the local bonding environment, the different in the how the electrons are sitting and pushing back on each other. It's probably the bonding environment that's actually doing most of the damping, but the phonons are completely damped down. And so functionally, this is an exciting area for developing new thermoelectrics. If we can dope this in a way that allows us to get electron conductivity while maintaining those damped phonons, it's a nice thermoelectric. And then on the dielectric side, we've done some follow-up work here where we've done some relaxer ferroelectric work that's also pretty
Zac, can you just clarify you mentioned the amorphous limit? Some people may not be familiar. What does that mean? Does that mean that the amorphous system has a the thermal conductivity as low as possible? Is this this known?
Yes. Yeah. So typically what you can imagine if you have an amorphous material. So let's take exactly the same elements and the same stoichiometry that we have in our crystal, but you just mix everything together so you have this amorphous material. At that point, because of the bonding environment, the phonons obviously are going to be totally damped because your modes are never going to be able to set up uniformly to be able to pass the heat through with just the phonons. And so that's typically considered, that's as low as you can go. Whatever that amorphous limit is, that's as low as you can go. No crystal's ever going to get there. What we see is that actually you can get there, and there are a few papers out there that suggest that you can actually get below the amorphous limit, which is interesting. I don't think that's been answered yet.
Hi, I have just a quick question on this. Do you observe any strong effect for the low frequency phonon or the acoustic modes?
I can't answer that. In this particular system, there are no clean modes. Like there's no one single mode that sets up, right? So the lower frequency are more common in a different system that we worked on with Rick Everett at UCSD. That has not been published. And that was, like I said, it was a different system. And we were able to find a few phonon modes that could be tied back to the kind of a sublattice dependence. So depending on if you had disorder on the A site or B site or both sites, we need to get around to publishing that. But in this system, we weren't able to pick out any particular mode that was clean throughout the system.
In general, it's very hard. I mean, it's very easy to affect the high frequency phonon, but it's very hard to touch the low frequency phonon. So I was just very curious.
Yeah, and that's why I say if the transport, the thermal transport that is there from the phonons is, those low frequency guys are still probably the ones that are contributing, even though they are greatly damped.
Yeah, thank you.
Okay, so the next step, so that was our first example of growing one of these things, but then we want to take a look at, okay, what happens when we play around in the systems that we're more familiar with, and we may have some interesting questions about exchange, complexity on that exchange network. So if we think in terms of a simple crystal with a uniform composition versus our systems that are going to have these multiple components where we're breaking the compositional symmetry, for magnetism, this is a pretty interesting route to take, because you're going to get something where your spin symmetry is broken. Each of these different sites, is going to be dependent on charge state and composition of what the spin contribution is. And of course, depending on what the nearest neighbor environment is, that's going to drive whether you have a preference towards ferromagnet or anti-ferromagnetic coupling. This is, again, this charge disproportionation and how charge sharing can happen. This is really, in my mind, one of the most exciting things going forward, trying to figure out what we can do with this. So just as an example, if we have, you would think in a perovskite, you have a 3+ on the A site, a 3+ on the B site, and then your -6 on your oxygen O3, right? You want to balance that out. What happens is, so say you've got a manganese sitting next to a nickel, that nickel will pull the electron over. But the nickel down here, if it does not have a manganese around, it will be in the 3+. So you can get these really complicated charge states and spin states, just depending on what your local environment is. So this is one of the challenges to you as the theorist, to try and figure out how to make a system, how to be able to handle this type of complexity and capture all of these possible states. So in this system, we're going to go to the 3D transition metals, and right there, the chrome, manganese, iron, cobalt, nickel. And of course, these have very exciting phase diagrams. This is just a nickel and the manganites, and you can have all of these different metal states, insulators, different types of antiferromagnetism, ferromagnetism, all of these coexisting just in the simple ternary system. So, what might actually happen if we mix all of these together? So step one is we're going to grow these things again. This time we're growing on three different substrates. So STO is a tensile strain. We're going to pull the lattice this way. LSAT is a very closely matched, so we're getting pretty close to what the bulk symmetry would be. And then LAO is smaller, so we're squishing in the plane and pushing out of the plane, changing that orbital. So we take a look at the surfaces, again, very clean, flat surfaces. These steps you're seeing are coming from the substrate miscut, so that's a single unit cell height that you're seeing on the LAO and STO. LSAT just tends to not have these clean terraces, but again, it's flat within with it far less than a nanometer sort of roughness. And so here are these different symmetries. So now, this basically says that not only are we able to grow these, we're able to grow them well on different lattice parameters, different substrates. So we'll do a couple of glamour shots here, doing cross-section TEM, zooming in. And again, this time we're going to do eels. This time we were able to do column resolved eels. And you're seeing, while you're seeing these different, all of these are lit up. What that basically is saying is you're looking down the column with the electron beam. On each of those sublattice columns, you have all of these elements. So that just means that we really are very well mixed, no clustering. Okay, then the unexpected thing that came out of this was
just before you go on, are these insulator? Are these all insulators, or some of them are metals, or how does that work? You didn't talk about that.
So today, I'll show you the stuff that's, so these and these lanthanum 5B systems, these are all insulators, but I'm not going to talk about it. Maybe in one of the other papers that we've got out, you can dope these to become metallic. And so that's doing your, basically doping that A site with hole doping is
okay. I was just curious about, I would assume these are Mott insulators though, right?
Yeah.
And so you said that there can be partial charge transfer, they can be in different valence states, but if they're Mott insulators, then you have integer valence. You can have different valences, but there have to be integer valence, right? On each transition metal site, right?
Yeah. So here's the challenge for you. Recognize that may happen on one microstate, but what happens, 3 unit cells over where the local environment is something different. And so it's really this idea of which of these kind of approaches are you going to use to try and flesh out what the functional properties of these things are. That's really the kind of the
but in your mind, can you imagine that there are little regions which are metallic? You could have partial charge transfer and mixed valence regions. Is that possible, do you think, in your mind, or not?
I think so. And some of that, it's very complicated because especially in this system, you can have charge sharing with these different elements also. And so as you're going through temperature, you may have different regions that are clicking over as you go down in temperature. The physics of one local microstate that may have been in a larger state, that local state all of a sudden goes through some kind of a thermal, thermally it wants to localize something that it wouldn't have at a slightly higher temperature. So you may have these different regions. So there's definitely multiple length scales that you have to figure out whenever you're, fundamentally trying to understand these. And it's a great question. I don't know. This is why I'm excited to talk to you about these things, right?
Very interesting.
So what we saw then in this particular system was we put this in and did some neutron diffraction on a film, and we saw that we had magnetic ordering coming up. And so it's basically, this is our background, our substrate kind of puts some noise on here, but we can say that the ordering probably starts somewhere a little over 150, but it's very clearly out of the noise as you're going down in temperature. So we're getting antiferromagnetic ordering on this thing along the half-half-half direction. So what's strange about that, if you think we've got this really disordered system and you've got 4 different, the local environment, you may have 4 different exchange interactions going on. So trying to understand how you go from that to some kind of a macroscopic percolated antiferromagnet is definitely a question worth asking. So we were working with Elbio Delgado on this, and what he did is he basically did this amazing literature search where he went through and he tried to find out, okay, if I'm going to make a model, I need to know what those different transition metals, if they're sitting next to each other through an oxygen bond, how do they want to couple and what would their spin states be? And what you're going to see, you see a few of these little asterisks here. There are certain systems, not all of these. Remember, these trying to mix just in a binary system is very difficult, and you can't get single phase. So a lot of these are going to be heterostructures and trying to understand what happened at an interface between two different materials. So he did this amazing literature search and pulled out what he thought were his best guess at what the exchange interaction and the charge states would be. So you can see that in the parents, we have both antiferromagnets with here Néel temperatures over here, and here ferromagnets with Curie temperatures. So we very clearly have a combination of cations that are both ferromagnet and antiferromagnetic couplings in this system. So these are the, oh, sorry, let me get rid of that. Sorry. So these are the different, if we're going to populate a model, these were the selected spin states of these 5 different transition metals. And these were the antiferromagnetic coupling, the energies that were given to these for these different nearest neighbor bonds. If you have a very keen and quick eye, you will see that the spin 3 halves, if we're thinking in terms of everything should be a 3+, then manganese should not be 3 halves spin and nickel should not be a spin 1. What was great was Elbio came back after this literature search and said, no, this is what it's going to be, because when these 2 guys are on a lattice near each other, nickel will take that electron. And that's why you get these particular spin states. And we did XAS to confirm this. And sure enough, manganese was pure 4+, nickel pure 2+. There's some small details here, but basically that was it. So that his predictions were confirmed with that. So that was the first nod where it's like, Elbio really knows what he's doing on this. He's then going to go in and model these. So he's going to look at the spin structure factor. He's going to make a 10 by 10 by 10 model. He also did a 12 by 12 by 12 just to confirm boundary issues. But the point is, starting off, you do what, the parents. So something so a lanthanum ferrite. So you populate this with iron oxygen bonds all throughout and let that cool down, watch your spin structure factor, and it turns on this value. You do the same thing with nickel. And it turns on at this value. So that gives you these 2 different temperatures. Now you chaotically mix the 5 that we've got in this system. And the prediction is that you're probably going to be somewhere around 200 K, just judging from where that sits next to these other 2 values. All right, so then we start thinking about how can we predict and figure out a way to control these systems. So what he's going to do is, we've been looking at the antiferromagnetic on this pi. You could also do that on 000 for, and that would tell you what your ferromagnetic ordering temperature would be. So what he's done here is we're going to change the manganese, right? The manganese you see on this, manganese always has a ferromagnetic preference. So whatever its nearest neighbor is, it's always going to push that into a ferromagnet. So let's control for that guy and see if we can tune the that exchange coupling in such a way that we can control the macroscopic properties. So the model says as you go from 20 to 40% manganese, you drop the transition temperature, but you still have this percolated antiferromagnetic network. Below that or above that manganese, you lose your antiferromagnetism, but you do turn on ferromagnetism. So you go higher and higher, 40%. You can see if we put all this together, basically you get a phase diagram like this, where you get this middle region at about 40% manganese, where you're going to have both antiferro and ferromagnetic coexisting with each other. So that was the prediction. Now Alessandro is going to go in and he is going to grow these materials. So here was what we started with. Everything's at 20%. Now we've upped this manganese 40%, dropped these down to 15%, 60, and dropped these all to 10 to keep our stoichiometry, keep that balance there. And just to show you the films we grew, again, these materials grow shockingly easily with PLD. And so we were able to grow really nice films without a whole lot of effort. And looking at the gross magnetization, this is temperature, this is moment, and we see antiferromagnet, what we had before. You dope that to 40%, you start to see some small amount of ferromagnetism coming in, but still a signature of antiferromagnetism, and then a strong ferromagnetism when you go to that 60% manganese. All right, so that's great. We've shown that the predicted this predicted phase diagram seems to match well with what we see in the laboratory. What's exciting then is when we start thinking about what's happening really locally on the lattice, right? So what happens when you have an element where you have a preference with, you have both ferromagnetism and antiferromagnetism, these different coupling types competing with one another. So one place where you might expect this to be interesting is in with exchange bias. And so what this is, normally you take a ferromagnet and you couple that, you grow that on top of an antiferromagnet. And depending on how you cool that, if you put field on it during the cooling process, and then you do your magnetization loop, you get this shift that's from the exchange, the magnetic exchange bias, right? The only place that this happens is in heterostructures. This is how people have been doing exchange bias. There was a paper not too long ago that showed that you could do this in a bulk crystal, one that kind of self-organized, but it self-organized into these layered systems. But the main takeaway to this paper was the fact that exchange bias must have some kind of a glassy state coexisting. You may have a little pocket of antiferromagnetism, but there has to be some glassiness in there. So in our system, this should be perfect, right? Because we've got this frustration built into the lattice. So if we do the experiment, let's start with the 20% manganese. This is where we have antiferromagnetism is percolated, but we have little pockets of ferromagnetism that are unpercolated. So you have these uncompensated spins sitting in there. We end up with something really bizarre. We get a vertical shift, and that's that uncompensated spin from that ferromagnet. And so this gives us kind of this new and bizarre sort of exchange bias response. Now, if we go to the 40% where we have antiferromagnetism and ferromagnetism percolated, coexisting with each other, there should still be these little glassy regions at the phase boundaries, but we get something that looks very much like that traditional exchange bias horizontal shift that we see in the moment. And finally, if we go to the 60%, we just get something that looks like a straight up ferromagnet without any of these exchange bias responses. So this was exciting because this was really the first monolithic 3D structure with this exchange, where you get exchange bias. And we know that we should be able to tune this further by playing around with those compositions. And again, you can get continuous control over these things just by moving a little bit of that stoichiometry, the one way or the other, dictated by, in this case, what the exchange interaction, which one of those elements you want. All right, so we're going to try something, we start with the perovskite. Let's try something a little more complex. Let's pop into the Redelson popper. My thought process here and why I was excited to try this was we know that electron-phonon couplings are kind of fundamental to setting up superconductivity in the layered cuprates. So this is why I wanted to try this. We're going to damp out those phonons on the blocking layer. Maybe that allows us to see some kind of a fundamental response on the copper oxide. So we're going to grow right down the middle here. We're not going to dope this yet and just see what we get. So again, we're able to grow really nice crystalline films. Here you see the film here, substrate, nice uniformity, very flat step terrace again, nice flat surfaces. And if we go in and we do the TEM on this guy, we get nice structure. But importantly, we also see that on those blocking layers, those A sites are fully mixed along, down each of those columns. And then our copper is fully confined to the copper oxide plane. And you might see what are these little spots here? This is an instrument issue. So praseodymium and copper have this very near energy. And so you get a little bleed through on the praseodymium coming into your copper image. You can see a little bit of the copper here. But really, they are completely separated, and we know that we're confined here on the copper. So that puts us right down the middle on the phase diagram expected to be. So we would expect this to be an antiferromagnet, and we do see evidence of this splitting in squid magnetometry. And also in X-ray linear dichroism, we see this offset between the horizontal and vertical as you go through that transition. And so we're pretty confident that we do have antiferromagnetism. So, really getting our hopes up here. Okay, now what happens when we dope this guy? So we're not 100% sure because we have both lanthanum and neodymium in our material, right? So how is that copper oxygen plane coordinated to the blocking layer? We don't know for sure. Well, at this point, actually, by the time we did this experiment, we had already made the materials, and we did actually know that it is coordinated on this side where you don't have the octahedral coordination, you just have that planar. So we would expect then from that standpoint that this cerium doping should be the way to go to get to our superconductivity. But just to cover our bases, we did the strontium also. And so here's the X-ray diffraction of our undoped film, the cerium doped and the strontium doped. They all look good. We had high quality films of this. Now we look at the transport data, resistivity. We're getting something. So our cerium dope, where we were hopeful, at least we can measure it all the way down, but you can see it does go insulating. The undoped is just basically an insulator up to 250 or so. The strontium doped was strongly insulating the whole time, basically unmeasurable. It was so insulating. So then the question is this just an issue with the oxygen stoichiometry maybe? And so we wanted to do a comparison between if we anneal this in ozone or hydrogen and see whether playing around with that oxygen content allows us to answer that. On the cerium, this is a cerium doped over here. This is as grown. If we hydrogen anneal, so we're trying to pull a little bit of oxygen out, you can see maybe we drop it a tiny bit more on resistivity. If we put more oxygen, if we really oxidize it, then we push it way up into basically unmeasurable insulator. Undoped, you see we have kind of this similar response where pulling oxygen out or pushing oxygen into it. And then strontium, there's just really nothing we could do to that guy to move it around. But we can say that at least with the hydrogen on the cerium doped, we did get it to go metallic. So these are two different annealing temperatures. So we can get this thing to go to metallic, but we never saw any of these go superconducting. And so I think that, we had some strategies here playing around with that, what the stoichiometry on that A site is, getting lanthanum off that site, maybe getting rid of europium or something else, may have given us some routes to getting to superconductivity. Of course, changing that rare earth composition. But, near term, what can we just try strain tuning, right? Let's try and get rid of the rumpling on the copper oxide plane. And so the way you would do that is maybe by trying to grow on a larger or maybe smaller, if you can get rotations in there, substrate. And so there's unfortunately a complication with that, or an opportunity, I guess. So these are 5 different substrates we grew on. This is going from the largest substrate to the smallest substrate. And we're seeing these little humps are the film peaks that we're seeing. And so you see this film peak, MgO really just has nothing, it's amorphous. Here's the scan date and the STO grow nice RP crystals. And then something happens here. This one drops off and we start to see, this drop. We're getting something cubic that's popping up. So this is what we see is when you're controlling the strain, you basically can't control it all the way, because if you have a certain seeding site on your substrate, you will end up getting a different crystal type growing. And so what we see is it looks like we've got a spinel. It looks like somehow this is flipped over and we end up with some kind of a cubic spinel. So let's try, and I want to stress again, this was before we had all of our data in. We were thinking that maybe what we need is, if we want a 20% strontium, maybe what we need to do is just make sure the mixing is a little better if we have it equiatomic with everything on the A site. So we tried this, and again, we got beautiful crystals. So now, look at this, we're up to 11 cations in this material. Depending on the substrate though, you get the Reynolds and Popper or this cubic state depending, and unfortunately did not superconduct. We haven't followed this up. It may be possible to put cerium here. Maybe this is the route towards getting this to superconduct. I'm not sure. I'm still hopeful that this is possible, but it's kind of evolved beyond this. So to close out, I want to just point out something that you all are very well aware of, and that's some of the difficulties and opportunities with these systems. So I'm going to call this the difficulty with many body problem, right? So the problem is nearest neighbors, especially in these correlated systems, both nearest neighbors obviously matter, but then your next nearest neighbors, maybe your next nearest neighbors also matter. And so we want to know, how do you simplify this so, a computer, even a supercomputer, can handle these sorts of calculations, trying to cool these down. And so not only do you want to capture all of the possible microstates, but I'm going to make the argument that the distribution of those possible microstates is also very important. And so
just one comment. I mean, when you were showing the previous magnetite related series, and you were talking about magnetism, you were able to explain everything with LBO through percolation. That means that the number of these microstates is really not many. That you really have basically two things percolating, and you really don't have to worry about these many microstates, right? Wasn't that a message?
Yeah. So I think he was able to pull that out, and I think that's true in that system. And I'm showing I am focusing on kind of the simplest, some of the simplest systems that we have. When you go to something where you're trying to see surface energy, so in particular, so let me give an example. So one of the areas where I see these particular materials being really exciting is doing things like catalytics and ion mobilities for batteries. And so in that case, those surface energies that you have, the complexity of that is going to dictate what your catalytic reaction is. And so being able to understand really what all of those different states are, that's going to be of fundamental importance. And so I think that there really is a need to understand locally what's going on. As we move these systems towards some of the directions we're going with, like topological systems, also understanding what your band structure, fully understanding what your band structure is doing, I think is going to be.
Well, that was my other comment. My impression, I didn't see the details of the theory work that you showed from LBO. My impression is this is done just from models of localized magnets. So you don't really need to know the electronic structure very much, because you assume it's just a multi-insulator and basically charge is doing not much, except for giving you a given valence state, right? But and so it didn't require some complicated electronic structure calculations at all, right?
So on that system, because we're focusing just on the magnetism, when we only have the ferromagnet and the anti-ferromagnetic coupling, those end up being the dominant thing. But understanding before you even get to that point, lanthanum manganite will actually, in the bulk, wants to have an anti-ferromagnetic coupling. You have to understand that when you make a film of that thing, it goes to a ferromagnetic coupling because of the change in the ion-Teller structure and what happens when you shrink it. So then when you put that next to, say, a nickel or something else, you need to have in your mind what's really going to happen with the local charge state. And so this is manganese and nickel. If nickel wasn't in there, then how's manganese going to interact at this point? What we're seeing, and I'm not showing this part, we can talk about this later. We're seeing some really extraordinary charge states in some other systems that we're growing. And this is where you can get chrome, you can get weird different charge states of chrome. Cobalt will go into some very, very charged states. And so if nickel's not in there, then suddenly manganese is able to interact with these different elements, and there's some kind of a hierarchy, right? So if you've got nickel in there, there are some local states where nickel is not a nearest neighbor with manganese. And so what is in there? So if it's a cobalt, the cobalt will then take that electron. If cobalt's not there, it looks like chrome will start to want to pull a little bit over. So understanding both the possible the effects of the local microstate, but also what the distribution of those microstates are is really important. And that's in this simple in the magnetism example that I gave, that's not a dominating thing. it mainly shows that LBO
Okay.
is really an expert on those transition metal systems.
Right, thanks.
So if we think, this is just to reiterate this idea of the microstate. So if we have a single ternary, if we're thinking of what's just manganese, oxygen to whatever the next B-site cation is, in a ternary, you know what that central element is, assuming no other defects. If you go to some idealized half-dope system, then again, you're up to something like 14 different possible microstates and some distribution within there. So you've got these, there is some, so around a nickel, there is some small probability that everything around there is a nickel. There's some small probability everything's a manganite. So then when you're working on your models, trying to figure out, do we just take the simplified, do we just take this highest probability state? And that's like, I think that's what you're getting at. And in some systems, absolutely go with the composite. That composite high probability state it may get you very close. When we go to strongly correlated systems, it may be that, or in particular, if you're trying to tune the energy, like surface energy composition, these little shoulder probabilities are going to become much more important. I think this is what I think's. So this is something where, maybe modeling right now can handle something like this up to some amount of voxel size. But now we get to something with like the quinary here, where we've got more than 1,000 local states, and then we've got overlaps between these. Anyway, you can see this is really the challenge. Do we just take the highest probability state, or do we think about what's going on in these little shoulder regions and how those overlap and interact with each other? So then kind of to close down, I just want to point out some of the functional regions that we might be able to address with these microelectronics and QIS. Because we can get these metastable states and we can tune these in kind of in a continuous fashion and get these crystalline materials, I think that, well, we're seeing that those are definitely some interesting areas, especially with spin glasses and spin textures. Energy, this is one, I think near term, this is the highest payoff that these materials have. So these are going to be for catalytic materials, ion conductivity, and of course some of this, can we make some of these thermal electrics because we damp down those phonons? This near term, this is where the big payoff is going to be as far as functional materials. And then advanced manufacturing, I put this in there because I think it's an interesting thing. If we can get to the point where maybe machine learning is tied into our synthesis apparatus, so that there's a feedback loop where the AI could kind of control functionally, it knows where it needs to get in a functional space, and it has multiple guns with different parents in there, and it can kind of mix these together. This is kind of pie in the sky. I think this would be an interesting area to look at, and we could maybe get this region where the robustness of the high entropy system, now we bring in the functional properties using some of these oxides or some of the other where we have an anion sublattice in there. So instead of just being structural, which is where we see the metal-metal bonded high entropy alloys, maybe we can move into a functional phase space for hardened materials as well. And with that, I'll close out and just here's some of our recent papers on these high entropy systems that I think I only hit on 2 or 3 of these papers. So there's definitely some more that we're working on. Thanks.
Well, thank you very much, Zac. This was super interesting. So now, are there any questions from the audience?
Yeah. Oh, great talk, Zac. Thanks. One question, when you showed the sort of overlapping distributions, that still is, yeah, this one, say, or even the previous one. I mean, your probabilities here are just based on counting. So that's just assuming there's no interactions preferring certain orders over others.
Yeah.
So becomes even more interesting to see, I mean, right now, if you have 50-50, the most likely is the same number of neighbors. But if you have a strong interaction preferring one over the other, your whole distribution might shift. So yeah. Things can actually become much more interesting.
Well, and so this is what I'll say here is the materials that we make with PLD, because we are in such a high or such an out of equilibrium state when we hit it with the laser, and it quenches so quickly that I believe, and from all of our microscopy and everything else, it looks like, at least with that particular growth process, you really do get completely mixed. You lock in the super highly disordered state. If you take that, and that's something, if had more manpower, I would love to be able to do this, take that film and heat it up and just bring it back and forth with temperature, try and get it to a point where enthalpy starts to come in and do exactly what you're saying, where we start to allow things to move and find their preferences. That is definitely a processing step that could be developed, more of an engineering step, but that could give you this control over what nearest neighbor compositions you had.
Right, and that might actually very strongly depend on what are the energy barriers between that you'll have to overcome. So I mean, this is all the excitement of non-equilibrium statistics. And
so if I can follow up on this, you may ask a question: what's the energy to flip two different elements in the slides, two different, for example, swapping nickel and manganese, like, or some of them. Now they don't all have the same charging state, but suppose that they did have the same charging state, two of them, some of them may have. So what's the energy cost? So this is very closely related to what they call inverted spinels. In inverted spinels, you can actually flip them at relatively modest temperatures of hundreds of Kelvin. This is something I learned from my friend Vladan Stevanovic from ORNL. He has studied this with Alex Unger. It turns out that the electrostatic interaction is what controls actually the energy to exchange them. And it turns out that I think, in some of these structures, you may not have long range order, but you can have some short range order, which is substantial. To follow up on what Marcus is saying, that it's not completely random, provided that this electrostatic energy that you're talking about is much larger than the thermal energy. But it could be that to really get a long range order in terms of any periodic structure, it's very difficult to achieve. So the type of short range order may affect physical properties, perhaps.
Yeah, the spinel, I agree, a very interesting system, and we've been working on that also because we had similar questions. So this was the first one we did. You'll see we just basically put extra iron into this guy. It shows some really interesting behaviors, especially with magnetic texturing and other things. But we went back and we haven't published this yet, but we've actually got this with just equiatomic. So we basically have all of these in here equiatomic with a 304, and it does show, depending on how we grow it and what substrate we're on, you can create you can control a little bit of that inversion. And basically your ferrimagnetism turns on at different temperatures, and you get this crossing point where one sublattice is maxed out in moment, and as you come down, this other sublattice picks up moment, and you do get a crossover in your magnetization. So I agree. The spinels are really, I think, a wide open area also, because the magnetism there is insanely, interesting and complex.
Yeah,
Any other questions?
My question is concerning the bring a more complex to the system. Actually, you only mentioned the ferromagnetic and anti-ferromagnetic coupling between magnetic elements, but there are something in between, which is spin candidate coupling. You don't mention about that. I wonder if that does exist, because you have a manganese, you have a chrome. Those are preferred, very complicated spin structures. But they couple with other magnetic elements. They could, and also iron, and also can be a spin canting state, depending on the distance between iron atoms.
Yeah.
So this can be more complicated. Yeah.
Let me point you to a really interesting paper specific to the L5B. That particular magnet one we had. It's going to be this lattice uniformity. So this was led by Matt Brelick in our group. And if you take a look at this is again those five Bs on that those 5 transition metals on the B side. what we saw was that actually structurally, this thing is unexpectedly uniform. So it picks a slightly orthorhombic distortion type throughout the entire thing. As far as we can tell with X-ray diffraction, lots of X-ray diffraction, there are not local pockets of one distortion type or another. It's really very uniform. So this is, I think what happens is if you want to get these canted in some of these other states, often that's tied into a change in what the, Jahn-Teller or some kind of a tilt or something else that plays with the orbital. So in this case anyway, at least it looks like the crystal structure is uniform. So whatever's happening there is uniform throughout. So you wouldn't get a small region of a tilted antiferromagnetism or something else. That being said, if you do go back to LBO's model, and he'll be the first to say this, it is a very simplified model. And so absolutely, if you dig down deep in there, and especially what we saw with the exchange bias behaviors, with some of these glassy behaviors that are going on, it's, I'm certain that there's all kinds of interesting local, especially at these coupling boundaries, where something, the charge could be moving energetically. These, the charge and the orbital and lattice are so closely matched at in energy in those materials that, there should definitely be something else going on there.
Could it be that the magnetism is much more local in terms of tendencies to local orders than the crystals structure? Because the strain fields are very long ranged. Mm-hmm. And so that it may be when you mix many of them together, because of relatively long range interactions in terms of structure, that they really basically all cancel out, and you have to pick one that you cannot. I mean, this is what I've heard from the literature, that these these alloys are very uniform in that structural sense, which I think from the theory modeling point of view is a huge plus. Yeah, that we could, we don't really have to consider very non-uniform lattices.
And that's in these oxides in particular, that's the key point that I keep bringing up. I think that when you make the model, the reason they're so uniform is because the electrons will slosh around a little bit to try and even everything out. So that's why you really need to know what your mixing is and what what those probabilities of nearest neighbors are going to be, because that's going to dictate what the charge states are, and then how that balances out to uniformity.
Okay, electrons sloshing around to balance this out is actually scary from DFT calculation point of view. But going back to Jan's question, I mean, you have different interactions locally. Even if your lattice structure is uniform, you still could get some non-collinear magnetism. Actually, you'd expect not really a perfect collinear magnetism, because you're no longer having the symmetry that would enforce it. On the other hand, you have this, I think it's a strongly layered system, so you might have actually very strong anisotropy in your system, countering this and actually stabilizing mostly collinear orbit.
Yeah, and so that first L5B paper, that was really, we were looking at that magnetic anisotropy of macroscopic anisotropy of the system, and there's very clearly a strong connection between that magnetocrystalline energy and how that tunes your that magnetic term.
I have just one quick question. You have talked about possible applications in thermal conductivity, but lowering thermoelectric material by lowering thermal conductivity. So have you tried any effect of vacancies? Because in the past, vacancies have been found to be very powerful in suppressing conductivity.
Yeah, so I think if you want to further engineer these, that's a great idea. And you could even go, depending on which system you're using, by creating oxygen vacancies, you may be able to push that into an electron. You may be able to get some double exchange or something. You may be able to get electrons moving. And that is right? That's what you're looking for. But we really haven't followed up on that. That's pretty far outside of our funding purview to go after thermoelectrics or even phonons.
Okay, thank you.
So I think if there are no further questions, this is, I think, a good point to close up. But Zach, we would like to follow up with this if possible. And maybe, if something comes to your mind, what would be the good starting point for some theory modeling? There are so many different, there is a broad canvas of possibilities that you painted here, but if you could come up with some suggestions, where would be the most interesting, specific examples that would be kind of consistent? Because, our project has some kind of limited focus, not so much on magnetism, but more on electronic states. And so, the questions that we could pose, but specifically, what would be some realizations, some particular examples which we could, contribute to, that would be very helpful for us, and maybe, could be a start of some collaboration.
Yeah, and so first off, I'm curious to see what kind of new approaches you all are able to bring to the table, either with machine learning. How do you train this thing, or how do you simplify from this? I know that was part of what was on GitHub. I was looking at some of what you were doing there, where you take locally what's going on and you assign that a value, and you you try to cross these length scales using that approach. I'm curious how, this is wide open, so I'm curious to see how you all find ways to include all these. But as far as what we're looking for, I think the lowest hanging fruit, if magnetism isn't quite in the wheelhouse and you're really looking for charge state, the most interesting thing is going to be with electronic states on a surface, specifically to catalysis would be my recommendation. These things have already shown some really spectacular properties for being able to do OER sort of reactions, even in harsh environments. Being able to develop those. So those are just random guesses people took a measurement on it, and they work very well. So maybe you don't need, already with a random guess, you don't need platinum group metals anymore, right? What happens whenever we figure out how to control those individual parameters, exactly what our crystal structure needs to be, which facet. So this is one thing I'm showing on the screen now. I think maybe I'm not showing this still. But being able to, with the thin films, we can actually grow on different substrate terminations. And so we could match back if theory was able to predict what the energy states at our surface were, we can go back in, I can grow a crystal on these facets, so we can individually isolate what the facet is, so we can get this really nice feedback between theory and experiment. And so if you're looking at charge state, I think that is where the big impact is going to be, is trying to understand, how charge sharing and distortion in these things, how that creates an environment that allows something like catalytic reactions to progress. It doesn't happen on the fundamental side, of course. Just answering the fundamental questions of what happens when these elements are next to each other, that is still very important by itself. But I think that's where the application is going to be, is catalytics near term. And in the bulk, it's then going to be ion mobility.
I see. Fantastic. So thanks again, Zach. This was very super stimulating, and so hopefully we'll stay in touch and continue the discussion, in the coming days.
And Marcus, I know you're upstairs, so I got to come up and bother you more often.
Yeah, certainly Marcus knows a lot of the theory side. Yeah, that's great. So we can also determine the charge state. That's we never invest. Mostly we just deal with the transition metal hydrogen alloys, but now we're adding oxide, and we do check the charge state.
And maybe I would make a suggestion. So if you're these single defects that you're looking at, say an oxygen vacancy or something, try putting hydrogen in there. What happens if you get a hydride on the surface? What happens if you put a hydrogen down deep in the lattice? How does that interact with the oxygen in the local environment? I say that because we've got some results that we're trying to figure out, and that's a very important question that, as far as I know, there's not a lot of modeling out there for it.
Fantastic.